Welcome to the first fourth seminar of the 2025 fall semester. My name is Kara Brugman. I'm a research scientist here at Force.
And I'm Kyusei Tsuno, also the research scientist at Force.
Today we have a talk from Klaus-Dieter Liss, who will be discussing to us some of the things that the HPT can do. But before we begin, I want to remind you that this meeting is being recorded. It will be available on YouTube afterwards, where you can also see all of our past seminars. You can also join our mailing list to be the first to know about our new videos, our new seminar recordings, our new seminar announcements, and of course, when registration will open for future events. We have three more talks coming up this semester, all from people at Arizona State: Liss Steinman, our very own Kyusei Tsuno, and the new Force faculty member Sibo Chen, who'll be starting his position in January. And of course, please save the date for the fourth winter workshop. This will be in person at ASU January 7th through 9th. And we are actually in the process of inviting speakers now. So hopefully we'll have an announcement out to the listserv soon about who you can come and see speak. And without further ado, I'll turn it over to Kyusei to introduce our speaker.
Hi, I'd like to introduce today's speaker, Professor Klaus-Dieter Liss. Klaus is a research professor at the University of Tennessee, Oak Ridge Innovative Institute at Fusion Technology and Materials for Extreme Environments Convergent Research Initiative. He earned a bachelor and a PhD in Germany, a bachelor at Munich, and a PhD at Aachen, focused on the neutron and X-ray optics. So his research focuses on the in-situ diffraction studies of metals under thermo-mechanical, and extremely environments. And today, Klaus will be talking about the high-pressure torsion process and some application for the physical property of the metal. So, Klaus, you can start.
Yeah, thank you so much, both of you, for this very nice introduction and the opportunity to give the presentation here. My talk today is metals under extreme characterization, physical behavior, and structural design under high pressure and after high pressure torsion processing. So I'm at the University of Tennessee, Oak Ridge Innovation Institute. You kindly introduced me already. Materials designed by microstructure. We all know that this is very important because the materials properties, they depend very much on their microstructure. For example, the mechanical properties. We know they depend very much on grain size, such in the Hall patch equation. When you make the grain smaller, the shear stress which you can apply, so the strength of the material, goes up with the square root over the diameter. And this is because of the pile up of dislocations at the grain boundary. And one dislocation pushes the next one and the next one. That makes, so to say, a super dislocation. And the number of dislocations which you can pile up, obviously it depends on the grain size. And typically half of the grain size goes to the top here, and the other half goes to the bottom. At the grains boundary, they're pinned and they need some extra energy to overcome. That makes the material hard. It's resistant to shear stress. So we also have dislocations already. They give you further work hardening because dislocations, they can be entangled with each other. Precipitates leads to precipitation hardening. And this is because of precipitates hindering the free movement of dislocation. And we have solution hardening. That's where a cloud of solutes is around a dislocation, for example, also pinning the dislocation down. The microstructure also determines the physical properties. For example, magnetism. And since we are talking HPT, I have here an example which we studied not so long ago with Amitesh Paul, where the magnetization changes, whether we have HPT's processed material or whether we look to the as prepared material. You can see the differences here in these curves of magnetization. So this is the magnetization, and the magnetization changes as a function of temperature. So this is at low temperatures, changes dramatically, and the character changes a lot. So these are all design parameters. Similarly, you could think about superconductivity and quantum phenomena. I won't talk about that today. Yeah, I like to talk about ultra-fine-grained nanostructured material. So when we make the material really nanoscale and nanostructured. You see here, this is 500 nanometer, and this is a HPT processed sample. This is 200 nanometer here. You see a lot of features in the grains and in the subgrains. So some grains, they were smaller than 100 nanometer, and the features therein, they're even 1 order of magnitude smaller. So we're talking tens of nanometers. And this can be achieved by severe plastic deformation. For example, using high pressure torsion. I will talk about that later. And what we want to do here is to study the properties and stress properties in this case, and also subsequent temperature evolution. So what happens to the material when we heat it? That leads to the overview of my presentation. I was asked to give a brief introduction to high pressure torsion. Also, we just call it HPT, high pressure torsion, for those who are not familiar with it. Then I will give an overview of neutron and synchrotron activities, which I do in my lab here and in the past 20 years, and selected examples. So one example will be on in situ high pressure and high temperature, now torsion, but therefore in situ. And then the characterization of high pressure torsion samples, as well as looking 1 or 2 examples about the temperature evolution of high HPT process specimens. So this was a real experiment. We have a Paris-Edinburgh cell here on the Wombat diffractometer in Australia. This was my student here. She did the internship, and they're cranking up the pressure by hand here. Just yeah, well, an anecdote. Okay, there are many methods for severe plastic deformation. One is high pressure torsion, but we also have twist extrusion, equal channel angular pressing, ECAP. So this is also well known in or commonly used because relatively easy to do. And then we have multi-directional forging, cyclic extrusion compression, accumulative roll bonding, ARB. This is also a very nice technique. And there's lots of these techniques described in this paper, where I also have this, the figures from. So I'm one of the co-authors of over 200 authors in this overview article. The DOI is given here. And it shows not just this one page of severe plastic deformation. There are multiple pages, like 5 or 6 pages, including roll bonishing. Roll bonishing has, for example, an application for making the surfaces hard. So what we do is severe plastic deformation at the surface, which is yeah, basically very similar to what we do in the bulk in HPT or ECAP, done on the surface in a thin layer, making the surface hard and resistant, corrosion resistant, stress resistant, and so on. Okay. Yeah, number 1 in that paper, if you remember the slide, is high pressure torsion, because high pressure torsion gives you very severe plastic deformation, a lot of strain, a lot of plastic strain. So applications of high pressure torsions are in the nanostructuring of simple alloys, so aluminum, magnesium, steel, and so on. And it can change the crystallographic order to disorder. We have studied that, for example, on titanium aluminide, which are intermetallics, and they disorder at high pressure torsion with severe plastic deformation. And this may be interesting even to study other phenomena like radiation damage, where you have an order to disorder transition due to severe or extreme environments. Then we also can, and I will show an example here, mechanically alloy multiple metals. So this is a slide here by Professor Kawasaki. She may be online, I'm not sure. And having 3 layers, sheets of material, like magnesium in the center and aluminium at the top, at the bottom, and then you start high pressure torsion for hundreds of turns. And eventually you get a nice mixture, and what's happening there, I may talk about it later. So you also can design multiple threaded immiscible composites. So having 2 materials which are immiscible, and you just swirl them together, twist them together. You call it twister, yeah? The twister is shown here. I took some pictures from your websites where you have successfully processed the consolidation of powders. So you make a powder compact here, and the other labs, Kawasaki and others in Europe and around the world, they're doing that as well. So you have a green powder sample, like you make a sample for sintering, but instead of sintering, you compress it together and shear together into a solid piece of material. Beautiful outcome of the twister, I have to say. Yeah, then there's the change of physical properties, which I mentioned already, and the design of microstructures through subsequent annealing. So a lot of things may happen, like recrystallization and recovery and other things, when you take this HPT sample and anneal it to higher temperature. We will see what's going on in some typical materials. So what we want to do is understand and make new materials with exceptional properties. All right, so this is my normal introduction to high pressure torsion, which I give without a primer. High pressure torsion, I said already in this figure here to the bottom right, we have a specimen which is then placed between 2 anvils, and that we see in the movie to the left here. So the anvil is closed and the sample is in between, and the bottom surface or the bottom anvil drives the bottom surface of the sample to the top surface, which in this case is stationary, and that means we get a lot of shear in the material. So we can see here in Megumi Kawasaki's paper how the sheets, the magnesium sheet in the center eventually dissolves. So here you see at the borders there's barely a mixture seen. It looks more homogeneous. And we talk about that later. So also from Kawasaki's research, which we do together, is we process the sample at room temperature at hydrostatic pressure around 6 gigapascal, and then we apply significant shear strain to give true nanoscale grains, obtain them after minutes. And the equivalent strain is the shear strain, which is gamma, divided by square root 3. So take the shear strain. This is just at a given radius. You go out and you rotate. So it shears in this direction in a cylindrical way over the height h. The circumference is 2 pi times radius. H is the height of the disk, and then the number of turns. So how many turns you do that. That gives you the shear strain gamma and gives you equivalent strain for the experts epsilon. So before HPT, the specimen typically looks like this, and after HPT, very much similar looking than the outcome of the twister. So we have the sample here, we have a fringe where little of the material flows out and seals the pressure cell during the processing. And very nice work here, typical properties done in Oregon State University in Megumi Kawasaki's lab is the increase of hardness as a function of shear strain. So we remember, here's the shear strain as a function of radius. And as we go up here in radius, out in radius, we see there's increased hardness. In the center, we have a singularity. There's, well, mathematically, there's no shear strain because the radius is 0. So in this equation here at the bottom. And then as you apply more and more turns, you get more and more saturated hardness shown by the blue color here. Right. So these are recent results to the left. We make new materials. So I cannot tell what this is before we publish. Comes shortly. But what we see here is a X-ray computed tomography, which has been done at UTK in our institute in collaboration with another professor, Penumado, and his postdoc, Stephen Young. So they did the tomography. They have the nice machine. And what we see there in 3D, the distribution of inhomogeneities. And again, you see in the center, it's very inhomogeneous because shear strain is low, and equivalent strain is low, it's 0 at the center. And then as you go to the border, you basically see already there's a transition from rough to smooth. Here from rough to very smooth at the edges. So we have a 3D volume which we can evaluate. But I only want to say there's a lot of heterogeneity introduced by HPT. Well, here another example is titanium aluminide. So take this part here. You see the edge, or something like that, the edge of the disc in cross section. You polish it, you cut it and polish it. Then we see this little fringe here, a little fringe to the top, or you see it at the bottom here as well. And this is the edge of the disc where most of the highest shear strain takes place. And we put it on a heating microscope, a high temperature scanning confocal microscope, which the University of Wollongong owns in Australia. And upon heating, we see that there's different evolution of microstructure. So different evolution of microstructure, this is different phase recovery and different stress state recovery and crystallographic recovery according to different applied, locally different applied shear strain. So the samples are heterogeneous. That makes them interesting for many studies. Well, we're doing research, so we have a few questions. Typical questions are, what are the phases in the microstructure and the stress states, and also the texture. Texture is already as a function of orientation, and also as a function of position, all these things here. How do they evolve upon heating? Yeah, are they heat resistant, or can we, well, what we see is stress relaxation, recovery, recrystallization, grain growth, depends on what temperature you are near. There may be precipitation in some of the materials, phase transformations, and defect kinetics, which is different than on normal materials, normal microstructures. So the HPT and the heat treatment can be applied for the design of the microstructure. And that's why we're doing the research. We want to learn something about the microstructure evolution and get kinetic parameters, thermodynamic parameters, enhancement due to lots of excess vacancies and so on. So material can be homogeneous, heterogeneous. I mentioned already heterogeneity in some of the materials, and multi-threaded. So this is where you have immiscible materials, immiscible metals, which twist into each other and they become very fine swirly structures. Right. Now let's come to what I do with diffraction. Since over 20 years, I'm running now projects about modern diffraction methods for the investigation of thermo-mechanical processes. That's about the exploitation of novel methods using both neutron diffraction and synchrotron X-ray diffraction, so large user facilities. But there's more behind. There's a whole lot of data analysis. You have to understand in reciprocal space what's going on, and you get maybe 2 hard drives full of data if you go to a synchrotron, and you need to separate and dig out, if you like, the microstructure information in reciprocal space. So we go multidimensional, not just the 1D XRD, we really go multidimensional, 2 or 3 dimensions. Then we have the time resolution. We look as a function of time, and that, of course, in situ. And we want to bridge the scales between the crystalline structure, the nanostructure, the microstructure, and the engineering structure. So we have to merge the disciplines between instrumentation. There's a lot of instrumentation technique in what we are doing. Material science, that's what I elaborated a little bit here. The physics behind, sometimes magnetism is physics, sometimes there's optics, which is physics. The engineering, so how do we process it? How we do tensile testing? How do we measure mechanical properties? And nowadays it's very important to do computer science. We use computers a lot already all of the time, but now there are opportunities to go with AI. Right. So what I'm interested in is metals under complex conditions, such as the behavior at high temperature, not just for HPT material, generally, like phase transformation, recrystallization, kinetics, I mentioned that already. High pressure, this is of interest for you, and I digged out one example where we went to the Spring 8 beamline using a carbide type press, and I will show these examples later in this presentation. So we get phase diagram and bulk moduli, and then in situ deformation of the material, such as thermomechanical processing, to get stress-induced effects, grain refinement, grain rotation. So we look also in the rearrangement of grains and orientations of grains that can be very, very unexpected. Not my talk today. And then we look to the deformation systems, like is it slip, twinning, is it martensitic transformation, or other. So we have typically multiple phases at high temperature, or sometimes here at high pressure, but then we don't have too much plastic strain. And here I have the zoom thing in the way. Yeah, I get it away. So I have crystalline, or this applies to crystalline material, but not only. We also can look to interatomic spacings in amorphous material, or even in liquids. Right. So what we want to do is to measure in situ the structure while we do the processing. These are pictures of zirconium alloy under tensile testing at the APS beamline, normal grain size. So I won't have time to talk about that today. This is titanium aluminide, which we heat up to 1400 centigrade and do diffraction in situ. So this is a false color, black and white photograph. And behind I put a diffractogram. And the setup is relatively easy. So you have an incoming beam at the synchrotron, which is fine bundled. Then you have a specimen. It can be in a furnace. It can be in a load frame. And we record the Bashir rings in the distance. Yeah, this is a Kleebler thermo-mechanical processor. I would love to see that in a beam one day. And what we do during the heating, during the operation, we do the diffraction with neutrons or with X-rays. Conventional characterization is you process the sample, you quench it, you cut it, and you study the cut surface with a microscope, maybe some XRD, which goes in a few micrometer, and so on. And then you start over with other processing parameters. So what we do is in situ neutron and X-ray diffraction. That means in situ during the heating or during the plastic deformation, or something is going on in real time, so we can get time-dependent information. And the question now is, do we want to use neutrons or synchrotron X-rays? They all have their advantages and disadvantages. So neutrons, they have a very different contrast and large penetration into the material. That's why we get a good grain statistic for quantitative phase analysis or for texture analysis, where you have to average over many grains. Not talking today has magnetic moment, and it sees hydrogen very well. Synchrotron rays, they are small, sub-millimeter, sometimes close to a micrometer squared or a few micrometers squared, and very brilliant. You have a lot of flux in this very small beam cross sections, and they're very parallel as well. That means brilliant. So we can look to the statistics of single grains with a high time resolution, because we can do fast movies. We have a lot of X-rays, and high reciprocal space resolution, because they are very bundled in very parallel coming in. So the scattering angle, if you like it, is well defined. This is just an example of attenuation lengths. Normal X-rays in the lab, they lie here. So this is in meter, this is micrometer, this is 10 micrometers. You see many of the metals, you go a few 10 micrometers into the material. While with neutrons, the neutrons, they're all here for these for these typical elements. So you typically have centimeters to meters penetration. And for some of them, you have a little bit more absorption. So you're not going that deep, but still much deeper than the X-rays, conventional lab X-rays. With synchrotron, we can go high energy X-rays, let's say 100 keV. So we also can go through the millimeter or maybe 3 millimeter of our samples. So millimeters here, this level. Right. We use the high energy X-rays at the ASF in Grenoble, at the APS in Argonne here in the US, Spring 8 in Japan, and the Petra 3 synchrotron in Germany. I've explained already the setup here to the right. Okay, let's now come to high pressure. Let's come to the topic. This is an example I want to give, just very briefly, where we have a titanium aluminide sample here in the center of a Kawai type press. So a very similar press which you have, this Ichiban. And the sample size is this. It's relatively small. You see here 1.5 mm or maybe 2 millimeter across. And the other things inside here, this is is a pressure medium, and you have heating elements. So with electric current going through these leads here, we have a heater, and we can heat up the material within that little sample volume. So what we found, we looked to the bulk moduli and saw also a transformation during the compression, a slight transformation from gamma phase to alpha phase. The percentage increases a little bit, and the amazing thing is that the alpha phase needs more volume than the gamma phase, And this is driven by a high ordering energy. Totally the volume goes down, but in the phase fraction, it can increase a little bit. It's like uphill diffusion when you do diffusion, right? Okay. What I want to show here is as a function of temperature now to the vertical and the phase fraction of different phases. So at ambient pressure, P equals 0, we have this dotted data. And you see the dotted data, they go here and here for the alpha and alpha 2 phase, which is a hexagonal phase. And the gamma phase is the ordered FCC-based phase. You only have the two phases. So the one goes up and the gamma goes down as a function of temperature. And eventually you have an alpha transverse. This is when the gamma phase disappears. Now, under high pressure, about 10 gigapascal, maybe went down to a little lower when we heated it, but that's what we applied, 10 gigapascal to start with. We see as we increase temperature, we get another phase. We get the beta phase. And this beta phase is a BCC phase. And it becomes quite abundant at high temperature. We don't need to go to melting here. Melting is this temperature here, yeah? That's when everything disappears. But it becomes quite abundant, many tens of percent in this temperature range here. And that makes it very interesting because this alpha phase is brittle, the gamma phase is brittle, but the beta phase is very ductile. So we have found a processing window for deforming, for plastic deformation of that material with a lot of beta phase at high pressure, while when we remove the pressure, it goes back to alpha and gamma phase. So I'm talking about this. This is a processing window where the plastic phase is abundant at high pressure and it disappears at ambient pressure, making the material stable at applications at intermediate temperatures, which are around 1000 Kelvin. If we had the beta phase already at ambient pressure, then we would expect more creep in the system. So that resumes a little bit what I said. Time is running. Let's go on. So let's look also to the Debye ring analysis, in this case for X-rays. So here are Debye rings from titanium 45 aluminum 10 niobium before and after heating and cooling. So we take the material, we have this diffractogram, these Debye rings, heat it up, and then we cool down and we get that. And you see already the stunning qualitative difference. Also, you go in the radius and you plot all the peaks in the radius. You can find probably all the peaks here, you can find there as well as a function of radius. But when you look to the azimuth, the azimuthal angle, you see a huge difference. If you look, and the huge difference is that these reflections here, this and these spots, yeah, they come from individual crystallites. While here on the right hand side, the crystallites are so small, and actually this is a HPT specimen. The crystallites are so small that we cannot distinguish or separate the reflections from the individual crystallites. There are so many diffracting that you get a continuous ring. Now we can go into detail already here. You see here's more intensity and here's more intensity and there's more intensity. And if you draw that up, you get a reciprocal lattice, and this reciprocal lattice is texture. Yeah, this also belongs here and something here. So you see that their orientations or their correlations between the different rings, and these correlations between the different rings here, they are orientation correlations. So it's a Blackburn orientation correlation in that material upon a phase transformation, or the Burgers or Potter orientation correlations. So all that we can read from just the static images here. But we make a movie over the whole cycle. And then we also can see how these the spots evolve and how they eventually move or sharpen or broaden on the Debye ring. That all gives information about the recovery process, about the microstructure evolution, phase transformation correlations, and so on. All right, so one thing I want to show here, the next slides will be some room temperature mapping of HPT samples. So I just resume in that slide. In real space here, if we have a specimen and we look to the orientation dependence, yeah, and it's stress-free, internally stress-free, then the lattice planes, spacings, they're in all directions the same, yeah? There's no elastic strain. In reciprocal space, the Debye ring, looking to a family of planes, is just a circle. Now, if we compress as here, then we can see that we get a strain ellipsoid because we compress in a vertical direction in real space, so the distances between the atoms become smaller, and laterally, according to Poisson's ratio, they become larger. So we get a ellipsoid. And the other dimension becomes larger as well. In a reciprocal space, remember, it's 1 over d or 2 pi over d in reciprocal space. That means it becomes shorter in real space in the vertical direction. It becomes longer in the reciprocal space direction, and vice versa. So in the horizontal direction, it becomes smaller. The scattering vector becomes smaller. And what we do, we sectorize the Debye rings. So this is just a little bit less than half a space of diffraction recorded, because we had 2 detectors. I don't show the other one. And what we do, we sectorize here in these 7.5 degree sectors in this case, and then look to the shift for each individual of them. Then we should see the ellipsoid. Okay, so now let's do the mapping of a HPT disk. This is a typical HPT disk, and we scan, the center is here, marked where all the lines cross, but due to the alignment, was a quick and dirty experiment, we scan a little bit below that center. And then we can say, remember, the torsion goes in the hoop direction, so the shear stress here is in the hoop direction, and here this line S is the local shear direction in that spot where I'm looking at, this blue spot. And obviously perpendicular to it in the radial direction is the transverse to shear direction. Now as we go, all these spots here, position to position to position, and make a line scan. So what I have here on the right-hand side, let's take the blue spot and we look in reciprocal space. So this is the strain now. We see this is the t direction. In the t direction, I have more positive strain on both in plus and minus, yeah. And also I have some positive strain in the shear direction and less in the direction in between. So this is a typical butterfly pattern, which comes after relaxing shear stress or after relaxing stress, after plastic deformation, because the slip is a little bit more complicated than just applying, because this experiment is not in situ. What we do is we strain in the HPT, then the lattice planes, they yield, or they should according to the Schmidt factors, and when we release, we get more relaxation in some direction and less relaxation in other directions. That's, well, roughly spoken, that's how we get this butterfly. So we can plot this as a function of x and y, the same x and y here. So this is the orientations now. Or we can do a coordinate transformation from here to here, go from the shear, go from the xy system to the shear transverse system. So I make the shear direction here and I make the transverse direction here. And that means you will see what happens. So let's play the movie. So I'm coming into the sample now. I'm going through and I see how the S and the T direction, they realign, because the T direction is always the connection from the point to the center of the disk. But when we look to the right figure here, now we are in, we see that the maximum and the minimum with respect to shear remain constant. So we can evaluate that. What I did is we record patterns here as to the right here. So diffractograms, Debye rings, and then we stretch them out as a function of azimuth, the azimuthal angle when we go around the ring. And this is the radius, basically, the value of the scattering vector. When we see the first reflection in the FCC, this is a 111 reflection, this is a 200 reflection, this is a 220 reflection, and then comes other 311 and so on. So now, as a function of position, so we can do that integrated over the whole ring, or we can sectorize it. When we sectorize it, we get those figures here on the right. So sectorizing, we get a lot of points, because for each position, there may be around order 100 positions, order of magnitude. For each position, we get 48 sectors, and they're all plotted here. So if I zoom into a small space here, point numbers, 1300 to 1500, then I see the individual cycles. So from here to here, roughly speaking, is one position. From here to there is the next position. From here to there, the next position, and so on, and so on, and so on. So I can sort them out into a position, an azimuth plot, map, let's say, yeah, where I plot here the intensity in the first row. Here I plot the strain, and here plot the width. And we see they're all very anisotropic with respect to the shear and the transverse direction. Or in the lab coordinate system, they have this S-shaped curve here. We can stretch that straight, and that's what we're doing as well. That's why we do the coordinate transformation. But this is half through raw data here. So we see the texture. Intensity is texture of the material for the 111 reflection, 200 reflection, and we have the others as well. So we can estimate which slip systems were activated there. For strain, we look to the residual stress in the material. So this is residual stress. It's not intergranular stress. Residual stress, which is orientation dependent. And we see it follows this S-shaped line where it reorients. Moreover, the full width half maximum, so that's not astonishing, right? What I said now. But what many people don't look at is the full width half maximum. So the peak width also depends very much on the orientation. And you may know people, they do Williamson-Hall plots and all these kind of things, where they look either into one orientation here on the XRD machine or many of the neutron diffractometers. So they're omitting all the other information, make a Williamson Hall plot from there. You may have limited information. Anyway, so time is running. This is another mapping of magnesium. I don't have much time, but you may have seen it because Megumi Kawasaki has given a talk, and this was one of our first mapping collaborations, which we did in 2019 at Spring 8. So as a function of position, we get all these diffractograms here, at least where something is filled, and we see that there's magnesium phase, and whoops, what's happening? And there's aluminum phase. So aluminum 111 and 002. And eventually, as we can see here, there's magnesium, magnesium. As a function of position here, the radius is given here at the bottom. We see eventually the magnesium lines that disappear. So we go into solid solution. So we have a transition region, a transition strain, which we can calculate, transition radius, where we go from the one to the other. And what happens there is we get, this is an average of 15 atomic percent of magnesium, which we measure here, while in the center, the aluminum only has 2 atomic percent of magnesium. So here, at the transition of that radius, we get a lot of alloying and solid solution alloying. And it has a very broad distribution, which we can see from the high order reflections here. So we have some grains, they have over 40% solid solution, and that's amazing. Okay, I have now time to go through neutron scattering. We'll skip a little bit. Oh, my thing is slow here. Because basically what we see with neutron scattering on different aspects, we also see here in this synchrotron experiment. So again, we do the high pressure torsion. How much time I have?
About 10 minutes. It's 12:50.
Yeah.
12:50.
Yeah, so I try to be rapid. So this is the setup. We have here a furnace with the hole in where the X-rays go in, and we heat the sample just to show how it looks on the beamline, and that goes further to the beam stop. And then we have detectors here and detectors there. And then as a function of temperature, which we apply in the furnace, we get diffractograms. So we can now look time resolved. So I'm playing a movie here. We have the time here on the left, and we have the temperature on the right. It's a little slow. And we see that there's an evolution on the Debye rings. We see now that phases are coming, so there are new peaks coming, and this is due to precipitation of a phase. And what we see later on is that the first phase disappears and the other phase becomes more abundant, and eventually at very high temperature, so this is the temperature profile, it disappears as well. Now you see it, there's this other phase coming. This is a T1 phase, precursor phase, and this is a T2 intermetallic in aluminum copper lithium system. And then at high temperature, we see there's this grain growth. So there's the transition from the smooth rings into the spotty rings. Now let me play the same movie again. I'm sorry, it's somehow computer slow. So it's coming now in big steps of time here. So I need to close the window. There's some noise. Yeah. So, and now you see a transition in the morphology on the Debye rings. So we have the azimuth here on the bottom, and we see, basically we see the recrystallization in this regime, and then we see the grain growth. From the number of spots, we can estimate the grain size, because the smaller the grains, the more spots you have on the Debye ring. And for big grains, you probably don't have, for single crystal, most of the time, you don't have a spot on the Debye rings. And this is microbeam diffraction. So we get this complementary information where we see the recrystallization on the bottom, and so the microstructure evolution on the bottom in reciprocal space, so in orientation space, and we see in longitudinal reciprocal space, so normal diffraction at the bottom, the vector at the bottom, we see the precipitation of phases, and we can study all that. So we see that here we have one phase coming and going, and the other phase then coming later and going later. So my time is running. We can look to the peak width, and the peak width goes down as a function of temperature. And this is the recrystallization process. So there's during recovery and recrystallization, when you do a Williamson-Hall plot, you measure the peak width, and the breadth of the peak is related to the grain size and also related to the intergranular strain due to intergranular gradients and stresses. We can look to thermal expansion. So this is thermal expansion, and we see there's a strain anomaly. I can subtract this straight line and get the figures to the right. And then I can look as a function of orientation. And as a function of orientation, I get this sinusoidal shape. So what I want to say here, and this is the point you need to take, is that we have residual stress as a function of azimuth, the azimuthal angle. The displacement is orientation dependent. That means we have a strain ellipsoid. And now for each of the points, I can go over here and plot a line as a function of temperature and see how that evolves as a function of temperature. So I see a collapse, beginning of collapsing of the strain amplitude. Then here it collapses to one line. This is the area of the precipitation of the first phase. Here we have the dissolution, the coming and dissolution of the second phase, and then it changes slope. This is where we, I think here we have the, sorry, it's a little fast now. We have the precipitation of the second phase and then changes slope, the dissolution of the second phase. So all that is shown in these multidimensional diffractograms. We can make a story out of that. So here's a storyline. We get residual stresses at the beginning, and we get precipitation of secondary phases. The residual stresses, they collapse. Then we have the dissolution of the second phase. We get the third phase and the dissolution of that other phase. And eventually we get large grain due to no hindered grain growth. Okay, we have published that recently. Just look it up, our newest papers, myself and Dr. Kawasaki. Let me give you one slide, the relevance of all that to force. Well, I'm very excited because that force facility and equipment is all a little bigger and a little bigger. So this itchy band, for me, this is complementary to spring 8 press. Also, it's offline, but it's bigger for material synthesis, for materials processing, and high pressure and high temperature. Maybe we can quench some of the high temperature phases, which I've shown before. And then obviously the twister. The twister, I would love to use it a lot, and probably many people, because it's also from the dimension and the parameters is bigger. So can we go to larger specimens at 6 GPa? We're processing at 6 GPa typically. Or what I wish is to process harder materials, that means harder anvils. Can we design, or have you designed harder anvils, e.g. for hard metals, like refractory metals, intermetallic compounds with physical properties. If you take Heusler alloys, they're very, very brittle and hard. Or even oxides and sulfides, they have also very different physical properties depending on many things in the material, many structural things in the material. With this, I would like to thank you. Sorry, it went so long.
Thank you for that great talk. It's very cool to see the torsion combined with synchrotron. Very cool. So we will maybe take one question. If we have a question from the audience, you can raise your hand, or you can type it in the chat and I can read it out for you. Okay, so Julia says, thank you for the great talk. I have several questions. Do the neutron and synchrotron diffraction have the upper and lower limits of the grain size detection? And in the case of an ordinary XRD, same question, I suppose.
Yeah, thank you so much for the comment. The grain size. So what typically people do is you can determine the grain size or the coherent diffraction volume size. That means between the dislocations with the Williamson-Hall plot. And there you can go into maybe, if you do it very well, into the 100 nanometer range. It's more suitable for the 10 nanometer range. With the microbeam diffraction and by counting the reflections on the Debye rings and working out how many grains are in the illuminated volume, which we know, we also can estimate the grain size. And we have seen something where, something happening. We have seen grain sizes in the 100 nanometer range with microbeam diffraction. So there, it seems that we have now a continuous overlap between the two techniques. Obviously, when the grains become too big, like 100 micrometers or so, or much bigger than the illuminated volume, then we go into statistical problems again.
Okay, and if you have time for other questions, I can keep going. But up to you.
Hello? Okay,
Hello?
sorry, I couldn't hear you.
Hello. Do you have time to
I'm
answer a
back.
couple more questions? If so, I can keep reading them.
I have time, yeah.
Okay, well, let's do, there's a couple more. Julia also asks, can the neutron diffraction or XRD measurements of the volume of the precipitates be accurate in a textured alloy? And are there ways to estimate this accuracy?
You mean the volume fraction? It depends very much on the texture. Volume fraction, you typically, and I see where a question points to, is that you look to intensity of the one phase reflections to the other phase reflections. And if you have highly textured material, these reflections can be non-representative because it may scatter somewhere else. The one phase may scatter somewhere else, but not into your detector. So in that case, you need to measure the full texture. You get a good model of the texture. Sometimes it's already good enough to have a two-dimensional diffractogram, as I have shown them here, because there are not so many different texture components. And I would say if you look into the future, some of our project is to use AI, where we have sparse texture data to get better information by machine learning on the texture of the material. This is to be done. That's very, very good and deep question for instrumental data acquisition. Yes.
Laxman Bada asks, in your presentation for Inconel, 200 reflection plane has more lattice strain than other reflection planes. Is it, sorry, the 200, is it typical for FCC alloys?
Yes. So the thing, very good observation, thank you. So when you do a stress strain curve and you put the stress and you measure the lattice strain of the different reflections, then they all have different elasticity. So the elasticity is a tensor. Single crystal elasticity is different for the different orientations, but also we have a lot of yielding. So once you become plastic, the effect of yielding in the 200 reflection is larger. So let's say it yields less, and you get more strain in the 200 reflection. Because some planes they yield. Yeah, when you have a FCC crystal and you have a 111 slip plane with a dislocation minus 110, and you put these dislocations in and move them and create more dislocations, then the lattice strain in the planes, which have a component in the direction of the Burgers vector, they relax a little bit, while the 111 plane does not change. So the slip plane distance does not change, while the other planes, they change upon yielding. Okay, there's a little change in the 111 plane because as you know, there are 4 111 planes in the FCC crystal. So if you have slip on one, it still affects the other 3 planar spacings. So short answer is yes, it's very typical that you have most of the stress response in plasticity, during plasticity, in the 200 reflection.
Okay, then last question. Ichiro Mori says, I think that neutron diffraction takes longer to accumulate a single profile than XRD, even with spallation source and compared to synchrotron X-ray. But how much strain stress resolution does it have?
That's right. Neutron scattering, we cannot do the micro beam diffraction because the beam already is much larger, so it's in a many millimeter regime. And even a full disk, so we have based the full disk in the neutron beam at J-Park in Japan. And the reflectivity, the statistics, counting statistics is weak. But what we have is good peak profile resolution. So we can measure the overall peak shifts as a function of temperature, of course, and the full width half maximum. And what we can see with neutrons is the decrease of full width half maximum upon recrystallization. So the things I have shown here, you can, apart from counting the spots on the Debye rings, you can do with neutrons, but the statistics, the counting statistics is much less because, and also the time steps, you may have 30 seconds acquisition time, while with X-rays, we typically do 1 second, but you can go faster. You can go 10 hertz, 10 per second. So that's right. High energy X-rays is more appropriate.
Thank you. Let's thank the speaker again for his time. Thank you for your excellent talk.
Thank you so much.
I thank you. Thanks
Thank you
for
everyone for
joining.
joining.